This video is going to describe how each of Newton's laws of motion are demonstrated, or we can use the word shown, in a video or other situation. So you know the first law is in the second and third. The first law says a body in motion remains in motion, a body at rest remains at rest until acted upon by an external unbalanced force. All right, so basically what this is saying, when it talks about the word motion, it means it's moving at a constant velocity. So we're going to look at how it's moving at a constant velocity for the first law. The second law says F equals ma. This means when I get my unbalanced external force, I'm going to have an acceleration. And an acceleration occurs whenever you notice a change in direction or a change in speed. The third law says for every action, there's an equal and opposite reaction. So for this one, we're looking for force pairs. So here's the situation. I've got a car moving in a parking lot towards its parking space, enjoying life. Everything's great. Music's up loud. It's a great song. Just moving kind of slowly, enjoying the morning. Oh, but then it hits the ice. Didn't see the ice. Panics, slams on the brakes, but the car's not slowing down. It's moving at a constant velocity towards the wall. Fortunately, it's moving really slow. So in the parking space, doink, off the wall it goes. And now it's moving backwards at some speed and it keeps changing. The brakes are off. Doesn't do any good. So just enjoy the ride. Then it gets on the parking lot pavement, hits the brakes, and the car comes to a rest. So let's look at this animation one more time. Notice when the brake lights are on and off. Here's the car coming to the parking lot, going ever so slow, enjoying the song. It's their favorite song, just moving right ahead. Oops, hit the ice, didn't see that. Panics, hits the brakes, doesn't do any good. Car just slides ever so slowly at a constant velocity into the parking space and then into the wall. Off the wall, it bounced, going backwards at some speed. The speed's not changing, it's very constant the whole time. Slowly moving off the ice, gets onto the pavement, hits the brakes, and comes to a stop. So let's look at the laws. The first law says a body in motion remains in motion and a body at rest remains at rest until acted upon by an external unbalanced force. The second law says F equals ma. The third law says for every action there's an equal and opposite reaction. So let's look at exactly what these laws mean by looking at when they're shown in a problem or when they're demonstrated in the problem itself, or in this case, the video. So when it talks about a body in motion remaining in motion, it's talking about a body moving at a constant velocity. And when it talks about a body at rest, it's talking about the body moving at a constant velocity of 0. So in other words, this object, this body, something's going to move at a constant velocity until acted upon by an unbalanced force. Oh, so it moves at a constant velocity until the second law happens. So where in this problem is the car moving at a constant velocity? So what I would type down is the car moves at a constant velocity along the ice as it moves towards the wall. Great. So in this statement, it's indicating what the first law is applied to. It's telling me this important phrase of constant velocity, because remember, it's all about the motion in the first law. So you've got to have that phrasing of constant velocity, and it's moving towards the wall. So this is where in this video or when in the timeline this occurs. It's really important to have that phrase constant velocity when you're talking about how the first law is shown in a problem, because constant velocity, that phrasing sets it apart from the other laws really easily and distinctly. So you need to have that phrase constant velocity. But it also happens at other times in this video, not just where I've stated in that sentence. The car moves at a constant velocity along the ice as it moves away from the wall as well. So as long as it's on the ice, it's also still moving at a constant velocity. Notice the phrasing constant velocities in there again, because that's what sets it apart. For me, that's what I'm looking for when I'm looking at answers. I've got to see that phrasing. The second law, when a car bounces off the wall, it changes direction. So this is a great statement for the second law because it talks about when the object, or sorry, which body we're referring to, what the force applies to, and when in our timeline, it's when it bounces off the wall. And how do I know it's an acceleration? Well, it's because it changes direction. So to show that there's an acceleration, a body can do, or a car in this case, can do two things. It can change direction or it can change speed. So when the car bounces off the wall, it changes direction. That phrasing of changing direction is important because that indicates that there's an acceleration without saying acceleration. Because we want to know how it's shown or how it's demonstrated or how it's indicated that it's the second law. So that's where I could apply the second law to. But that's not the only time. Where else in this problem does the second law apply? I'll pause for a moment. Well, that would be when the car is moving away from the wall, it applies the brakes and its speed changes. And I should probably add when it's moving away from the wall and it's left the ice, it applies its brakes and its speed changes. So again, I got to have the object, that's the car. I got to have where in this video. Well, when it's moving away from the wall, it applies the brakes. Okay, I saw that. And how is this an acceleration? Well, its speed changes. So either the direction changes or the speed changes, but you got to mention one or the other, or maybe both. But that's what separates the second law from the other laws really distinctly and clearly. The third law, for every action, there's an equal and opposite reaction. So we're looking for pairs of forces that are pushing against each other. And so that occurs kind of obviously in the beginning, or a little more obviously in the second part of this. But at the collision with the wall, the car pushes on the wall and the wall pushes on the car. So this is kind of an interesting phrasing the way it's set up. Collision with the wall, and we know the car pushes on the wall and the wall pushes on the car. So it's the car and the wall that are the objects. And this is kind of an interesting format of A does something to B and B does something to A. So that's kind of how the third law will always read out. It's just a matter of plugging in what the objects are that you've identified. But it happens another time in this video, and it's not so obvious as the first time. Or I should say it's less obvious. I don't know if it's always obvious, but it's less obvious. And that's when the car applies the brakes. So when the car is moving away from the wall, it applies the brakes. Friction from the tires push against the road, and the road pushes on the car. Or on the tires, maybe, I guess I should say, instead of just the car. But, so when the car is moving away from the wall, it applies the brakes. So that's the object that the third law applies to, and when in our video. And now we need to describe this as kind of like A on B and B on A. So friction from the tires pushes against the road, and the road pushes on the, well, it says car, but I think a better phrasing would have been, and the road pushes on the tires. That would have been good. So when describing, either demonstrating or showing, whichever word you want to use, where the laws are applied, for the first law, it's important to have the phrasing of constant velocity because that implies what motion really means. In the second law, we're identifying where there's an acceleration. So either it changes speed or it changes direction, or it could do both in your statement, but you need to state when you know that there's an acceleration occurring. And in the third law, you're talking about two forces that push directly against each other, and that's when A is on B and B is on A. So it's kind of a standard format for what that looks like. There are other forces that interact without physically touching each other. There's action at a distance forces, but we don't need to worry about those yet.